All right, so let me first like get a little closer to what kind of things I want to be talking about. So first of all, what is low-dimensional topology? So of dimensions 1, 2, 3, and 4. So a manifold, if you don't know what that is, it's a space, it's a topological space that's locally homeomorphic to Rn. So basically, like the surface of the Earth locally looks flat, so it's locally a plane, but the sphere, well, the Earth is kind of not a plane, as people have realized at some point. So surface is a nice manifold. So I kind of hoped, who has seen manifolds before? So it's like,
who has or who hasn't?
Who has? So like I want people to move, so everybody raise their hands. So okay, so for those who haven't seen it, are you happy with this? Sort of. That's kind of where I'm going to take it from. So I'm going to draw some more pictures. That's the nice thing about low-dimensional topology, because you can somehow see things. And so the main punchline of my talk is, in a very bizarre way, you can kind of see everything in dimension 2. So, right. OK, so well, or it's not called a big problem, but so a motivating problem, or even better, a guiding problem, let's call it guiding, is the classification of, well, manifolds of dimensions 1, 2, 3, and 4. So, and so, you know, as a mathematicians, you always play. So, in my opinion, at least as a topologist, you always play the same game. You define something, and then you try to see how many things there actually are. And so, well, in this case, manifolds are something that appear kind of in nature. So, if you will, and well, you might wonder how many things are there. And well, so the easiest dimension is, of course, well, okay, let's put in some more restrictions. So I don't want to be talking about all manifolds, but so we want to have some properties that make things well, easier. So we want compact manifolds, connected manifolds, and let's also say oriented manifolds. So, and usually closed, which means no boundary. So basically, well, what these things mean, connected means there's only one, it doesn't have like more than one pieces that are completely different. Compact basically means it has like a finite extent. Closed would then mean there's, you know, you cannot really run out of it. You just run around it infinitely many times. And so maybe, like, let's see, let's kind of see step by step what's known about this classification problem and what's not. So, so in dimension 1, so what kind of manifolds are there that say we want all the closed, compact-oriented manifolds with boundaries? So there's not much left. So there's the circle S1. So it's just this guy. Can actually, that's kind of an elementary exercise. If you just know the definition of manifold, and you know some integration and differential calculus, you can somehow figure out that this guy here is the only thing you can have. So it gets a little more interesting in dimension 2. By the way, if we have algebraic geometries here, dimension always means real dimension, so not that we get confused. So in dimension 2, So closed, well, so all surfaces, so that's two-dimensional manifolds are called surfaces, and they're classified by their genus. And genus means basically, so a surface, let's draw a prettier picture. So there's the surface of genus G, which is the sphere. So there's one thing. And so for G equal to 1, there's going to be the torus, so surface of the donut. And so then you can keep going by just basically adding more holes. And so this would be, well, a genus, well, how many, depending on how many holes you draw in this picture, that would be a genus G surface. So and these are all compact, orientable, or oriented, connected surfaces. So in dimensions 1 and 2, the classification is completely known, and that's like, it's been like that for like about 150 years. So this classification goes back to 1800 something, so it's like really old and classical. And so you might think that surfaces are done. They should be done, like should have been done a long time ago, and why are people even thinking about these things anymore? But surprisingly, if you spend some time in topology or, well, I don't know, any kind of mathematics, I don't know where surfaces don't appear. So it always seems that they come in some way. I mean, so in algebraic geometry, there are still like problems about moduli spaces of whatever complex curves, and so I don't know. So surfaces, just from as topological objects themselves, are quite easy, but so they somehow capture a lot of structure. And well, then let's go a bit higher here. So surfaces are done. And so in dimension 3, so like we notice, first of all, a problem. So 3 is kind of considered low, but so can you, like, how do you think of manifolds, three-dimensional manifolds with this property? So somehow it's kind of three-dimensional space is kind of nice, but so already, so there's the 3 sphere, you know, which is kind of the unit sphere in R4. But if you think of, so, and you can also think of that as like a one-point compactification of R3, so which basically means look around you, and no matter what direction, no matter where you look, somehow it's supposed to be the same point at the end. So I don't know. So I'm kind of, it's one way to, I don't know. That's kind of already something. I mean, you can't really see it as a whole, right? So you kind of have to imagine that there's something somewhere, and you have to know where to put it. And well, but overall, the classification is more, well, say a lot more complicated. So as soon as you go higher than 2, then, you know, there's not a nice little list. So there's not a single number that you need, and that tells you like what object you're looking at. So it's like a very, very complicated story. But still, well, but let's not say still, but at least people know roughly what to do. So basically things like geometry and group theory play a very important role. So you know, somehow the type. So you can kind of start. You can study 3 manifolds by cutting it into pieces that have a simple geometry, and that level. So the fundamental group basically tells you a lot about the three manifolds. So there's, especially in recent years, there have been like big advances in these fields. So which basically made like three manifold topology is very, can be tackled very efficiently if you're good in like these things. So kind of the flavor of three-dimensional topology. There's no complete list, but so there's, you probably know this famous Poincare conjecture, which tells you that everything that should be the three-sphere actually is the three-sphere. And yeah, that uses a lot of this here. So there's none of this, but a lot of this. And, but yeah, so that's the story in dimension 3. And so just for completeness, so that's just, so from dimension 4, so in dimension 4, it's just a complete mess in a way. So there's, so that's actually, so that's where I come in. So I try to do this for a living. And so the very big mess comes in because there are kind of two ways in which your manifold can be locally homeomorphic. Well, you can say locally homeomorphic and locally diffeomorphic. And then there's like transition maps. And so in all the lower dimensions, this distinction did not really do any. So like you get the same result in the end. So if you like only consider homeomorphism or diffeomorphism or smooth or not smooth, it doesn't matter. So in the end, you get the same results, as you can already see from if here the fundamental group doesn't really see any non-smooth behavior. But so in dimension 4, it starts to become very, it starts to be like very, very complicated. For example, so let me just mention. So there exists a 4-manifold curly R4, which is homeomorphic, but not diffeomorphic to R4. So that you might have heard before. So like just so the simplest manifold in any dimension is the Euclidean space. And so in dimension 4, even that is kind of, even there it's a difference. So if you ask for something to be homeomorphic to R4, not the same thing as being diffeomorphic to R4. And so that makes like 4-manifold topology very, very complicated. And the worst part is actually no one has a real idea like what to do. So everything, so like whatever worked in low dimensions doesn't work. So I don't know, people are just building 4 manifolds and trying to see what properties they have, and then they kind of try to see patterns. And someone says, I see this, then 2 weeks later someone comes up and says, that's wrong. So there's something which, so it's kind of been like that for 20 years now. And so as far as smooth manifolds are concerned, not really much you can say. So there's no good general theory of smooth 4 manifolds in dimension 4. So now let's say like one thing about the higher dimensional world. So now you might expect that. So we went higher and higher and higher, and things got worse and worse and worse, and this should keep going, but it kind of doesn't. So somehow from dimension 5 on, so the classification problems well, they translate basically into algebra and homotopy theory. So the keywords are here. I don't know if you want to look something up on Wikipedia. Surgery theory and the Escoborism theorem. So these are two big theorems that basically tell you that if you look at manifolds that have dimension at least 5, then it gives you a set of tools that you can put your hands in and kind of try to get a list or try to somehow enumerate like all manifolds that you're looking at. So like, yeah, one catch. So actually, starting from dimension 4 on, you would have to fix a fundamental group before you study anything, because there's this problem about no one ever being able to classify all finitely presented groups. It's one of these famous unsolvable problems, and somehow it happens that from dimension 4 on, you can get any fundamental group that's finitely presented. So in a very precise sense, in dimension 4 and higher, you cannot classify all smooth square manifolds, but fix a fundamental group and try your best. Okay, so now I could go on about this for, well, until the end of the talk, but that's kind of not too much of the title of the talk, so I'm going to stop that here just to, now, hope you now have like a picture of like why low-dimensional topology is kind of different, and that actually each dimension has somehow its own flavor. Now let's see how we can get things into surfaces. So, okay.
So we assume the high dimension, like this dimension more than at least 5, is it studied a lot, or is more like a sleeping field?
Well, so there are, so usually, so just writing algebra and homotopy theory, so it doesn't mean that things get completely easy. So, but so people have, so usually you will find, so there are classifications of simply connected 6 manifolds, or something like Q-connected 2Q manifolds, or something like that. So people have worked out a lot of things, and then like these exotic spheres in higher dimensions. So you can kind of classify all manifolds that are homeomorphic or diffeomorphic to spheres. So people have, so that field has been studied, but it's kind of not exhaustive. I mean, so usually, if your fundamental group is complicated, then you have to deal with algebra over complicated non-commutative rings. And so people kind of, I mean, mathematicians only do the things that are kind of easy for them. So unless you have to classify certain manifolds with certain properties, you don't do it. But if you have a reason, then you kind of have a toolbox that you can use. So, but let's not try to classify, but let's just try to visualize things. So, and so there's one thing that is also very classical, and it's kind of Hilbert diagrams of 3 manifolds. So, let's see. So I think I'm going to just write down how you can picture the 3 manifold, and then I'm going to tell you why, or how you can get there. So any closed and so on 3 manifold Y can be described by a couple of things. Well, let's write down a Hegat diagram. Well, it says up there. I'm going to just write HD from now on. So Hegat diagram is a triple usually, and so where the following thing. So is a closed surface and so alpha is a collection of G. Well, okay, let's draw this surface first. Let's maybe draw a genus 3 surface. So an alpha would be so these are each, so there's G things in here, and each thing is a simple closed curve in the surface. And so, for example, they could be something like this. So there, each alpha curve is an embedded circle inside your surface here. And well, you have G of those, and so they're supposed to have the property. So they're pairwise disjoint. And if you remove them all, is a sphere with 2G points removed. So, okay, maybe does everyone see that, or maybe not? So maybe like the baby case. So if we just draw like one curve and remove it, so you might just as well kind of remove the whole neighborhood of the curve. Right, so and would be, so if after we cut out the curve, so what kind of remains is this like cylinder-like thing, and you can also, we're topologists, or at least I am, so we can kind of push it around a little bit so that it becomes a sphere with two curves removed. Okay, so that's like one set of curves in the Hegat diagram. And actually, so you can assume if you have any set like this, then up to a diffeomorphism of the surface, you can actually always draw it like this. So this part of the diagram is, if you want, you can take it like that if you don't want to imagine complicated things. But so now, so beta is kind of the same. So that's kind of, it's a collection just like that, and so only the collection beta could, you know, if you kind of now draw a different picture of your surface, you could also draw the betas like that. But so the thing is, in relation to the alpha curves, that's where it gets interesting. So, for example, if we choose to fix the alpha curves like this, the betas might look something like this. There might be one that goes like this. There might be another one that goes like this, and well, there could also be, oh, what else? Oh, it's maybe, which one would be nice? Could go around here a couple of times, and go here. Well, so come out here, here, and somehow you have to find a way to get back. Comes out here. Yeah, okay, that's why you know. Okay, you learned an important lesson now. You should never try to draw a complicated Hegat diagram if you have none pictured. So let's start over and draw a simple one.
Because you will get stuck.
Yes, you will get stuck at some point, or the picture will look so bad that you and your audience will.
What you're describing, does this mean that there is a homomorphism, self-homomorphism of the surface that brings one to the other?
Yeah, basically. Okay. So yeah, so that's, if you think about this normalization, right? So you could also, you know, apply diffeomorphism of the surface such that beta is standard. So in a way, it's, you know, the surface, the diffeomorphism would give you.
There is the standard system of the alphas, and then you twist around the surface and whatever you can get.
Exactly. So basically, so these are the alphas, alpha 2, alpha 3, and well, so then let's be really simple. Okay, let's put it like this. So we have beta 1, beta 3, 2. So and actually, so the order of the curve is not really relevant. And okay, so now I drew a diagram, and so I claim that this diagram describes a three-manifold, namely S1 cross S2. So that's a three-dimensional manifold. So it consists of like this simple manifold and product with this. So basically, and it's not too hard to visualize. So you can kind of just think for each point on the circle, you have like a two-sphere. So you just take a sphere for each point. Yeah. So this is probably a more complicated way of thinking about this manifold. But so the useful thing is that you can do that with all three manifolds. And so the way you do this is by, well, one way to do this is to do Morse theory. I don't know if anyone has, well, let's make a poll just now. So I'm gonna background, so let's see, well, existence. So I'm gonna write down a little sentence here. So my FBA indexing Morse function with with unique okay, so let's see. What of that sentence do we know? So I'm just going to point at things. So who has heard the words Morse function before? There's a couple of those. Then index is, I guess, also fine for the same people. Self-index, okay. So let's roughly say what this is. So what you want to be doing here is so that also kind of explains like how you would get things into surfaces. So we understand surfaces. So and the pre-images well no, so the regular level sets of functions are surfaces. So if we take a three-manifold and just take some smooth function, some smooth map to the real line, and so well, if you just imagine an open set of R3 here, for example, then you learned in like sometime in the second year or first year of mathematics that if you take the pre-image of a regular value, which would be a regular level set, then this thing would be like have a nice structure. So in like one of the basic things in differential topology is if you take a smooth map, then you take a regular level, then that's going to be a manifold of dimension 1 lower. So if you start with a 3 manifold, you get a surface. So right. So that's the basic idea. So we understand surfaces. We want to understand 3 manifolds. So we can try it with functions. So let's just look at a function and see what we can do. So what we need is a nice function. Yeah, a nice function so that we can play the following games. I still have one blackboard left. So let's draw our 3 manifold as kind of something that does not look close to a 3 manifold, but and then we map it over to the real line. And so we know, like, if we like fix so if we fix one value, then so the inverse image of that thing will be so. Okay, so if we assume that y is a manifold which is closed and whatever, so then this means that these fibers are they will also, or these level sets will also have to be surfaces of the type that we considered. So they will be in this list somewhere. So if you fix some like regular level and you look at the pre-image, you'll see a surface inside your 3 manifold. And so you might look at another that picture. So if you look at a different value, then you also see a surface. Yeah, it might be a different one. So for example, this was a genus 3 surface, this was a genus 2 surface. So, but then, so another basic differential topological fact is that, so if you find such a situation where you have 2 surfaces that are kind of not the same, and you kind of see what's in between, so you kind of just go level by level. And so if you would not have any critical values in between, then these surfaces would have to be the same. So that's basically just follows from ordinary differential equations. So you can kind of, if you don't have a critical value in between, then your manifold cannot change. So there has to be a critical value C somewhere in between. And so now we can kind of ask these. So so I wrote lots of things here. So if you just pick a random function and you know that it has a critical point or a critical value, then this doesn't help you that much because there's a huge variety. So there's a whole field called singularity theory, which kind of tries to classify critical points of smooth functions, or well, it's part of singularity theory. So like just that doesn't help you that much. But so the thing is, like if you look at a generic function, it will have only nice singularities. So it will, so if you're so if you have a Morse function, which are these nice functions, so then if C is the critical value, is the value of a critical point P, then locally you have So your function will look something like this. So that's, since we're doing 3 manifolds, so this works in all dimensions, and it's kind of it's a very important tool in topology in general, so Morse theory, Morse functions. So locally you have a normal form which tells you that you can find coordinates such that your map looks like this quadratic polynomial, and there's only like one invariant, I mean the number of minus signs. And that's called the index. Of f at p. So, right, so if we have this Morse function, we can, so the critical points look like this, and from this local model, we can kind of also, we can use that to understand how the topology here actually changes. So if we go from here to here, so we know that, so, okay, how can we visualize this? I should have drawn a little more space here. Okay. So there will be a surface in between that looks like, okay, this is going to be that picture. Okay, I apologize for this picture, but I don't have the time to redraw it completely. So basically what you should see. So this is going to be your critical point P. So that's the fiber over C. So the level set will not be smooth. It will have a singularity. This local model tells you that it kind of looks like the conical thing here. And so what happens if you cross the critical point?
What happens is that simple curve gets pitched, right?
Exactly. So what happens is you'll see actually from this point you can do some tricks to get like one curve here, and if you get closer to the level, that curve gets smaller and smaller, and so somehow inside here, so this will actually trace out an embedded disk, so the curve gets smaller and smaller as you go by levels. At some point it's just a point, then it will open up and like go down, meet these in like 2 points here. So that would have been an index 1 critical point. So okay, so I mean I cannot explain Morse theory altogether. For Morse functions, as above. So now what you can do is you kind of start in the bottom, and so if you only have like a unique maximum or minimum, so then you know that at some point you'll see 2 spheres, so below that it's going to be a 3 ball, and if you go up, so you kind of keep adding these curves. At some point, you know, you will have reached the highest genus, so that's self-indexing tells you first the genus keeps on going up if you have the critical points, critical values, and then it will go down again. So, and you know, if you have such a Morse function, which is known to exist, you get a Hegat diagram. So, or Hegat. So, right. So you would kind of just keep track of these curves in the middle, and they would kind of flow down to your surface in a way. And so in the intermediate surface, you will definitely have these G collections of G curves, and you get it's like some from above, and some from below, some from above, and that will give you a diagram that looks something like this. And right, so okay, so that's maybe like two okay, so what you know, I know this was very sketchy if you saw it for the first time, but so the basic idea you should get from all of this, you know, there's a way of visualizing three manifolds in terms of surfaces, and the way to do this is by looking at functions and studying functions. So that kind of, you know, you have the target dimension is one-dimensional, level set dimension will be source dimension minus target dimension, so surface. Okay. So we had 50 minutes plus 50 minutes plus questions, right?
Yeah, so you have like
10 minutes left, I guess,
yeah,
right?
good 10 minutes.
All right. So, okay. Right. So let now.
This is for three manifolds, right?
This is for three manifolds, right? So, and I think, yeah, I should definitely mention something about four manifolds. And so now let's do that. So, and there are like yeah, okay, maybe one more thing. So about these diagrams here. So okay, so this is such a diagram describes a three manifold, and all the three manifolds can be described that way. And well, what happens if you have two diagrams that have the same that describe the same three manifold? Well, how do the diagrams relate? So that's known. So and it, not surprisingly, it comes from studying one-parameter families of functions. So in a way, like the whole question, you know, if you want to classify three manifolds, so classifying three manifolds up to diffeomorphism is the same as classifying these Hegat diagrams up to whatever moves there are known. So if you want, you can kind of base your whole, so if you want to classify all three manifolds, just play around with Hegat diagrams, and in the end it should work. But so of course things are not that easy. So Hegat diagrams can be complicated, and especially so surfaces themselves are easy, but these curve configurations are kind of not. And if you know, try to play around with these things for a bit, then you'll find out very soon that things are not as easy as they seem to be. But still, so using Hegat diagrams, you can do a lot. So there's like in the last 10 years, especially, there was a huge thing called Hegat-Fleur theory, which uses like a lot of complicated machinery to construct invariants of three manifolds out of these Hegat diagrams. And yeah, you can have a whole lot of fun. Actually, I was talking about that like 2 hours ago already. Yeah, it just came from a different talk. Yeah, okay, so that's three manifolds. So now for four manifolds, so there are like two ways that could be mentioned. So so there are things called trisection diagrams. And so now I'm going to be very brief. So this is like something very recent due to Gay and Kirby. And so what they do is they study maps now from four manifolds to R2, and now so a pattern should emerge. So again, you know, so we understand surfaces, we want to understand four manifolds in terms of surfaces. If we map it to something two-dimensional, then the level sets will be surfaces. So try to find like good functions, nice functions that somehow allow you to, you know, keep track of like what are the level sets, how they are related. And so what this gives you. So if you study like the right kind of map from a four manifold, then you will get something called trisection diagram, which looks almost the same as the Hegat diagram. But now you have three. So of curves, and in fact, so there's some compatibility conditions. So in a way, if you look at a good map from a 4-manifold to a surface, then you can kind of squeeze out this information, and that describes the whole 4-manifold. But so it describes it in such a special way that, so if we just like block 1, then what we see is actually a Heger diagram of some 3-manifold, but it's supposed to be a very special one, maybe some connected sum of S1 cross S2s, and that's supposed to be a special diagram too. But yeah, so let's ignore that. So in a way, so if you want, you can also describe like closed 4-manifolds in terms of diagrams that look like this. So kind of understand all of low-dimensional topology by just looking at curve configurations and surfaces. So in a way, so manifolds from dimension 1, 2, and 3. And 4. Yeah, so that's kind of, plus there's also a set of moves. So in a way, it's really all there. So maybe let's just draw one example. So if we just draw a torus, we need one curve in each set. So that would be alpha, beta. Now we could do something like this. Take this as gamma. And this would describe a complex projective plane. So how, you ask? I can't tell you. So it's in a way a similar thing. So you have this function, and this it has some critical value somewhere, and if you keep track of it appropriately, then you'll get this. So yeah, so that's one way to do this.
So wait. So for 3-manifold, I can follow what happens. I guess. I mean, there is a self map of the surface to itself that belongs to the pair alpha beta, right? And you just you fill up two surfaces, and then you glue it together like that gluing map, right? So is there something similar?
Yeah. So basically, you would take your surface times a triangle, and then along the edges, you would kind of glue like an interval times the solid handle body according to these curves.
Okay, so it's pretty similar.
Yeah. So then this compatibility condition tells you that like where you glued like twice some connected sum of S1 cross S2s, and then there's a theorem that tells you that you can uniquely fill them in. So yeah, now see, so I actually could tell you how you build a 4-manifold out of that. Okay, yeah, so that's one way to do it, but that's kind of somewhat not the way that I did it all the time. So there's a different description, which was a little, well, I mean, so this is very recent. I mean, so this is all like 2011 or 12 or something like that, and so it's still not really, known how useful these diagrams are, but they are there. And so a couple of years earlier, people had like slightly different ideas. So there's something called surface diagrams of 4-manifolds, and that's due to Jonathan Williams, who also came up with the name. So this diagram has a surface, so it's a surface diagram. And so these things, again, so these are derived from special maps in 4-manifold to the 2-sphere. So, and they look like this. So there's again a surface, and there are some curves, C1 times CK. But now, so they can be a little more random. So okay, so like the first curve might, for example, be this one here. So these are again simple closed curves. Such that, so like for you know, in the Heegard diagrams and also the trisection diagrams, we had such sets of curves, but so they were kind of like the genus. If the genus was G, then we had G alpha curves, and they were supposed to be pairwise disjoint. Not the case here. So the only restriction is that, like a curve intersects the one with adjacent index in at most one point. So this means, for example, that the second curve might be like this. And so the fourth curve then should, the third curve should intersect the third should intersect the second in one point. So we could, for example, take this one here. And let's see. Let's just draw a nice diagram. So okay, let's take this as the first, this as the second, this as the third, and this as the fourth. So and so the indexing is cyclic. So this means that k plus 1 is supposed to be 1. So basically, you kind of start with one curve, then kind of keep looking at sequences that intersect the curve, that follow this pattern, and at some point you get back to your original curve. So this describes a three-manifold, a four-manifold known as also like this. So it's there's like one problem with this surface diagram study. So this is kind of it's a very simple four-manifold. The diagram does not look that bad. Well, here somehow it's also not such a complicated four-manifold, but the diagram doesn't look too great. So, but still, what can you do? So these things. So I've been studying them because these were not there yet, and I thought it was a great idea. And so maybe like what would you do with these diagrams? I mean, so you want to understand four manifolds, and maybe like just to name one thing that you can prove out of these. So like one result that I proved in my thesis is that so if you have a closed four manifold, smooth, no, that's like this. So let X4 be a four manifold, and now it gets a little technical with a surface diagram of genus at least 3 derived from a null homotopic map. So these things always exist, so it sounds like a purple sentence by now, but so it's no really restriction. It's no restriction. So then the homeomorphism type of X is determined by the homology classes. So in H1 of the surface. So why is that interesting? So I mentioned that. So in 4 dimensions, it's kind of it's a difference whether you ask if things are homeomorphic or diffeomorphic. XBA. I should honestly say simply connected. So simply connected four manifold. So if you look at these things, and you have your way of putting this into a surface. So in terms of curves on surfaces so you can ask, so the like most natural thing is like two things are the same if they're isotopic. So like if you can like move one curve into the other through embedded curve. And you know, there's a huge difference than asking, you know, you have a homology class for every curve, but the difference between homology classes and isotopy classes is complicated. So, you know, for example, in this picture, so you have this curve, C2 and C4, and you can see that they bound something. So there's this like a thing that looks like this in between, if you kind of move your diagram a little bit. So you would have C4 on top, C2 on the bottom. So this would mean that C2 is equal to C4. So yeah, so you could kind of then look at the diagram where you replace C2 by C4. So the diagram C2, C3, C2, this would also describe some manifold. And actually, so in this case, what does it do? So I think this diagram will describe a different four manifold, unfortunately. So that's just because we were stupid. So in fact, we can actually, so there are more interesting ways where you can kind of change some curves in the diagram and not change the homeomorphism type of your four manifold, but produce something that might not be diffeomorphic. And actually, so this difference between isotopy and homology, so there's, well, one key word. So there are the so-called Torelli groups, and so what is that? So you can look at like the diffeomorphism group of the surface and look at its connected components. So like a diffeomorphism, so isotopy classes of diffeomorphisms, and so they act on this vector space, and it's a symplectic. Well, there's some kind of a symplectic form on there if you know what that is, and you know, so there's a natural representation of the mapping class group on the symplectic group, and so the kernel is this Torelli group. So these are the diffeomorphism, isotopy classes of diffeomorphisms that act trivially on the level of homology, and they exactly measure the difference between this isotopy and homology story here. So even though these diagrams look horrible, so somehow maybe hopefully sometime in the future you can prove that there's some actual relationship between these like exotic smooth structures on four manifolds and these Torelli groups. So then it might make sense to look at four manifolds in this way. And yeah, so I think I'm over time already, so I'm going to stop here, and if I haven't bored you enough, you can ask me some more questions. Thanks.